Welcome to my presentation of our work towards faster reasoners by using transparent huge pages, which is done by Johannes Fichte, Norbert Mantei, which is myself, Julian Steckliner, and André Schiedler. I briefly give a motivation and a very brief summary. So, as a motivation, there's many tasks of automated reasoning, for example, verification of hardware or software, anytime optimization problems, which give a better result the longer you let them run, and time-bound nightly jobs like analysis or verification, where in a given amount of time we try to squeeze in as much computation as possible. The question behind this work was, is there a way to improve all of these in an easy to consume way? Because there's already solutions, so as a related work, you can improve algorithms or data structures of solvers or automated reasoning tools, which give a high benefit at the cost of high analysis, research and implementation costs. And then there's one-time improvements. There, for example, is improving the memory layout, which requires to change a few lines. There is prefetching memory by adding a few instructions, which is typically 1 or 2 lines. Or in this work, we present to use huge pages, which basically requires you to recompile your tool once. And that's relevant for most of the distros, except, for example, Red Hat Enterprise Linux 7, because they enable huge pages by default for the whole system. So, a very brief summary is, if you use huge pages instead of small pages, then you get a speed up of an average 10%. Depending on the benchmark, it can be much higher. And this is a summary of how you achieve this. So, the first box shows you how to check whether your system supports it. The first command should give you a result always or advice. The second line shows you how to monitor whether you actually use huge pages and how many pages are actually used at the moment. The second blob shows you how to do this with administrator privileges, so you can install a package to easily modify the system settings to use the overall system settings for your tool as well as all the other systems that are running on your machine. Or, and this is the contribution of this work, you recompile your tool statically once. And there's a Docker file from the merge.stat repository which you can use to do that. So you use the command with your build command and then tell it to statically link against the modified glibc that comes from this Docker container, which for each allocation tells the kernel to use huge pages if possible. And then finally you can invoke your tool with the environment parameter glibc thb always equals to 1, and it will use transparent huge pages. We would love to hear about your experience with this and whether you get the same speed up for tools of your domain.
Hello everyone, this is Rahul, and today we are going to talk about phase transition behavior in knowledge compilations. This work was done with Professor Subhajit Roy and Kuldeep Singh Mead. So let's first talk about knowledge compilations. Now, knowledge compilations are tractable yet succinct representations for propositions formulae. And the idea here is to first generate an efficient compilation for a given formula and then use it later to answer queries quickly in an online fashion. So, for example, queries can be model counting or enumeration, which are actually exponential in the original CNF or DNF, but they run in poly time and size of the compilation. Now, this technique finds use in many areas, including formal verification, model-based diagnosis, and probabilistic reasoning. While a number of representations have been discovered in the past, we are going to look at some of the popular ones, DDNF, SDD, and OBDD for phase transitions. But the general behavior actually extends for all knowledge compilations under DNNF. Now, let's look at a bit about phase transition behavior. So, phase transitions are usually concerned with a sudden change in the behavior of a property of interest for an object pertaining to variations with respect to a control parameter. Now, a popular example is water, in which states change in temperature. Now, this behavior has actually been observed for many more randomly generated problem instances. For example, in the NP complete class, we have KCNF SAT, CNF XOR SAT, QSAT, and many such problems. What's interesting here is that the complexity of solving the problem is also seen to peak at the same parameter threshold regardless of the algorithm used. And we call this as phase transition behavior. And in this study, we will see how phase transition behavior is seen for knowledge compilations uh, for the randomly generated KCNF formulas. Now, a classic example of phase transition behavior is for SAT for KCNF problems. So I will not go into much details here, but in this figure, on the x-axis, we are drawing clause density, that is number of clauses divided by number of variables. And on the y-axis, we have the runtime. And here you can see in the blue line that near clause density 4.3, you can see that the runtime of the solver increases tremendously as compared to nearby clause densities. And it's precisely at the same time that the phase of KCNF changes from SAT to unsat. So this again is an example of phase transition behavior at the time of phase change. Now, the study of phase transition behavior was very instrumental in getting a deep understanding of KCNF problems, and even it has been very influential in the context of other CSPs as well. It was much later that their explanations came. We hope that our work here will inspire similar efforts in the future for knowledge compilations.
In this paper, we looked at solving satisfaction problems using large neighborhood search. So large neighborhood search, or just LNS, is an effective local search method for solving optimization problems using CP. But that means that in order to solve a satisfaction problem using LNS, we must first turn it into an optimization problem, which we can do by softening some constraints. So here, when I say softening constraint, what I mean is that we replace some hard constraints by constraints for penalty functions, and then try to minimize the total penalty. So for example, let's say we want to solve the car sequencing problem, which is a satisfaction problem. We can either do this by using a hard model and normal CP search, or we can try to soften the model and use LNS. In this plot, we can see the runtimes on the y-axis and the number of solved instances on the x-axis. If we use the hard model, we can see that we can only solve very few instances. But if we use a soft model, we can solve most of the instances that we looked at here. However, we can also note that the runtimes are actually pretty high when we use the soft model, even from the start. So what this means is that a soft model in LNS can sometimes solve more instances, but it actually usually comes with a high runtime. The main reason why we see a higher runtime is that when we use soft constraints, they actually give us very, very little propagation during search. And this just means that we have to search more, and that just takes more time. So in this paper, what we wanted to do was see if we can improve the propagation that we get in a soft model. So for doing this, we propose what we call non-failing propagators, which are a way of keeping some of the propagation of the hard constraint that we would otherwise just remove when we soften constraints. So the idea is that a non-failing propagator gets the prune values that are inconsistent with its constraint, so just like a normal propagator, but we switch it off right before it can cause a failure. So by using these non-failing propagators, we can get propagation that drives the search towards satisfying the constraint, but still have a soft model, and therefore be able to use LNS. So if we go back to the car sequencing problem, we can see that if we take the soft model and just add non-failing propagators to it, we can get about 1 order of magnitude improvement in terms of runtime, and we can also solve more instances. So as it turns out, non-failing propagators are actually easy to implement and can sometimes drastically improve the solving of satisfaction problems via LNS. We saw sometimes that we could get a 1 to 2 orders of magnitude improvement in terms of solving time. So if you would like to know more about this, please listen to our full presentation or have a look at our paper.
Hello, my name is Lucia Groleaz, and I will speak about an article we wrote with Samba NDA and Christine Solnon. The article aims at solving the group cumulative scheduling problem using an algorithm which combines CPO and ACO. First, I will give some introduction. Then I will describe more precisely our problem. After that, I will speak about the additional complexity brought by the group cumulative constraint. Then I will describe more precisely our algorithm which combines ACO and CPO. And finally, I will give some conclusion. Our problem consists in a set of jobs which must be scheduled on a set of parallel machines. In the example, there are 9 jobs, and we must schedule the jobs on 3 machines. Our goal is to minimize the sum of tardiness of every job. In the group cumulative scheduling problem, the jobs are partitioned into groups. Here there are 4 groups: the yellow one, the blue one, the pink one, and the green one. Then, once we have a schedule, we can say that a group is active at a time t, if and only if some of its jobs are started and some others are not yet ended. For example, at time 5, there are 3 active groups: the blue one, the yellow one, and the green one. The blue group is active because job J8 is started and job J6 is not yet ended. Now, the group cumulative constraint ensures that at all time t, the number of groups that are active at that time t is lower than a given limit denoted L. Here, for example, the maximum number of groups that are simultaneously active is equals to 3, and this maximum is reached at time 5, for example. The main contributions of our paper are a constraint programming model for the group cumulative scheduling problem, an experimental study of the complexity brought by the group cumulative constraints, a theoretical result, which is the following one. If we have the sequences of jobs on each machine, then it is NP complete to find start times that respect the group cumulative constraint. This result is important because scheduling problems are often solved in 2 steps. In the first step, we find a sequence of jobs on each machine, and in the second step, we compute the start times of each job. Then what we often do is to take a job into sequences, and we try to move it elsewhere in the same sequence or in another sequences. But now, finding a valid schedule if we have the sequences of jobs on each machine is an incomplete task. Finally, we introduce a new algorithm which combines CPU and echo, and we show that this algorithm outperforms other algorithms on that problem.